Thank you, thank you. I've got some friends in the crowd, but it's really great to be here on such a lovely stage. Although I do hope everyone read the description for this talk. It might be a little misleading, the title, if you're expecting software. This is going to be a hardware talk. I really hope there's no disappointed product owners in the audience. This is a great event, and it couldn't happen without the sponsors. But let's get straight into it. So for those who don't know me, I'm Drew. I am a software engineer at Bankwest, and I consider myself a full-stack web developer, but I specialize in front-end and design system stuff. On the side, I really enjoy doing visual art with code, so procedural art and fun animations. And I love making projects and showing them to people. This was me in 2023 doing a talk about an IKEA lamp that I hacked. It was good fun. Now, I love software as much as the next engineer, but and you can make all kinds of stuff. Like, it's super great, whether it's tools or art. You can make tons of stuff, except it's all constrained to the digital. Basically, everything you create is going to be behind a screen. And it's really hard to make tangible feeling softwares. You can do it, and great user interfaces feel like you can interact and touch them. But in general, it's hard when it's all on a screen. Now, things that feel tangible to me, stuff like books, records, tools, physical things, they have some significance. I feel like I value them more. They're more substantial. And another piece of context to this is I needed a hobby that didn't involve sitting in front of the computer. So I was on the lookout. Now, I started seeing some interesting stuff pop up on different platforms, YouTube and Twitter. Hardware engineers that were making aesthetic tech. They're making hardware look really beautiful. And I was intrigued. This is, I love aesthetics, but I'm also deeply technical, and I love learning how things work. So I started seeing these. Also, this kind of stuff, objects that have some kind of digital aspect to them really interested me. They don't have to have a purpose. They are just people making cool stuff. We don't have to have a use case or have it generate money. It's just creating something that exists in the world. There are companies that I am inspired by. One of them is Teenage Engineering. They have great user interface, very tactile products. And they do a lot of work in audio, but they also have other projects that they work on. And a bit of an odd one for inspiration is IKEA. Obviously, the original lamp that I hacked. But I found out that IKEA did a collaboration with Teenage Engineering back in 2020. It was this box, this cube-looking lamp. It was brighter than the sun. It didn't really make sense in a lot of ways. I don't think it sold very well. I bought 4 of them, but it got discontinued shortly after, which I was kind of sad about, because it is something that I think looks really cool. It's a little audio reactive, so it has some cool animations, but it just doesn't really make sense in terms of a product that gets sold. So I was intrigued by all of these different things, and I wanted to make something kind of similar. Learn the skills to be able to produce stuff like this. Now, I knew I needed a project. I learn best when I have a goal that I'm working towards, and I'm not just absorbing knowledge and facts from scattered different domains. I also didn't want to get kind of distracted by the endless creative possibilities that starting something from scratch and building an object would allow for. So it needs to be simple enough that I can actually get it done. Now I figured, hey, this product got discontinued. I really liked it. It would be a good first project, but I want something a little challenging, so let's make it 5 times smaller. So we're trying to recreate this, but 2 centimeters wide. It's definitely not something you can buy off the shelf or even buy the components to make off the shelf. It's something that needs to be built from the ground up. So that is the goal. Now, a little bit about yourselves. I think, give me some nods if you would consider yourself a full-stack developer. I think it's a pretty common it's a pretty common job description, and in that we cover a ton of different skills. You don't have to be experts in all of them, but you might cover front-end, deployment, back-end, databases, just a lot of different skills that you need to pull in at different times. So my pitch is, why not make yourself a super full-stack product developer? And take those skills and push them one step further so that you can actually bring digital experiences into the real world, create physical objects, and have this entire stack covered. OK, so let's get going. Now, you might have heard this quote. Very popular. Any sufficiently advanced technology is indistinguishable from magic, Arthur C. Clarke. But I don't think you've heard this quote. Electricity is magic. I'm being so serious. Just what would magic look like if it existed? It would be a mysterious force. You would have to study how to interact with it and how to channel it. You might have massive tomes of knowledge that you'd have to read through. Basically, that's what it is. We are creating, by working with electrical circuits, we are creating pathways for this mysterious force to be channeled into something useful. And there are so many spooky effects that it can take. So why would you not kind of want to be a wizard, gain those skills and be able to interact with this mysterious energy? So that is skill number 1, electronics. And to tap into this world, you will need a bit of an understanding of the interaction. So you've heard of voltage, current, and resistance, and they interact in different ways. So you're going to need to get an intuition. There are a lot of analogies, so people can kind of relate them to water flowing through a pipe, or maybe air pressure, or I've heard of chains and pulleys interacting with components, but they all have caveats, and they're all exceptions. So I would suggest, if you want to learn and get an intuition, just approach circuits and look at how each of the components is getting interacted with, how voltage affects current, how resistance affects voltage, and you will build up this kind of intuition. There was a giant tome that was recommended for me. That's not it. There we go. That's it. Yeah, OK. I'm seeing something else. But this thing was massive. It contains reference to all kinds of components and concepts. But you can also just watch YouTube videos. That's pretty good, too. We're not starting from scratch here. There are building blocks that circuits are made of, resistors, capacitors, transistors, and you can make really complicated things out of these building blocks, but that would introduce significant complexity. So if you're building software, you're not going to write everything from scratch. You're going to use libraries, and this means that your projects have less risk of bugs and issues from mistakes that you've made, and they're less complex to manage in future. So same concept. This is just the hardware equivalent of libraries is something called integrated circuits. So little microchips that contain a circuit in a package. And there's tons to choose from. So they might cover logic like charging a battery at the correct rate, or translating between one protocol to another. And part of this group of integrated circuits is something called microcontrollers. And it's basically taking the functionality of a computer and putting it on a single chip. And they're very cheap. So let's get back to the project. What we're going to need to recreate this thing, the original lamp was 16 by 16, so that's 256 LEDs. We're just going to go 4 by 4. So we'll need 16 LEDs, a microcontroller, something to power the LEDs individually, some way to get power into the system, so a USB-C connector, and then we're also going to need some supporting components, so resistors and capacitors. Just a little bit of info on resistors. They can, if you have a component that has a specific requirement of voltage that is coming in, so a resistor can help get your input voltage down to that level. They can also help smooth out signals going into input pins. Capacitors are also trying to smooth out spikes in voltage. And when microcontrollers are doing different processes, they can sometimes pull current, and capacitors will discharge a little bit of current to allow that to be a smooth process. This is a fun part. It's basically, you get to go online shopping, but like with the most complicated online shopping website ever. It is terrifying. And then you're looking for components, and you might find one, and then you got a data sheet that's fully in Chinese. But there's a couple of, you'll get used to it. You have to figure out your main requirements. So what exactly do you need the component to do? What are the limits that you're trying to push it towards? And then you basically just filter by price and availability. So that's actually quite fun once you get into it. This is our, this is kind of the logical diagram of what we're doing. So we've got a USB-C giving power to both the LED driver and the microcontroller. The microcontroller is sending data, telling the LED driver what it wants the LEDs to do. And then you've got a ton of different leads connecting the driver to the LEDs. Now, if you prefer AWS diagrams, I've got one of those. But this is what we would actually work with, when we're designing it. So our USB-C is down here, and you will download like a definition for what the component needs from the internet, and then you've got all these pins that you need to logically connect to different places. So maybe it's a 5-volt input, maybe you need a resistor, and the data sheet will tell you kind of these requirements. But you just go along, this is our microcontroller, kind of defining what you need. And YouTube is a great one. Looking at like example builds, people going through their schematics is really good. Here's our LED driver with the inputs coming from the microcontroller and the outputs going to the LEDs. And then down here, we've just got a bunch of LEDs. So these are actually, this diagram isn't just for show, it's actually defining connections in the program. I'm using KiCad, but then those connections will be used when you're building out your PCB later. Okay. Now, electrical projects sometimes look like this. This is an Arduino project connecting different modules. You can actually buy integrated circuits, ICs, that come fully packaged with all of their supporting components. And those are called modules. And then you have like platforms like Arduino that provide access to microcontrollers with ease of programming and standard libraries, stuff like that. But I always found that it feels similar to a low-code or no-code platform. So it's like you can do all this stuff, but once you encounter any degree of complexity, it just starts getting unwieldy and unmanageable. So same thing here. When I was trying to do electronics in the past, I would always find that my projects would never feel finished. And so the missing piece to that feeling, the solution was really PCB design. So skill number 2, we got to learn how to design PCBs. This will allow us to connect components in a much smaller footprint and for much cheaper. And they look freaking cool, so why would you not? So just quickly how they work. It's a PCB printed circuit board, and you have footprints, exposed pads that the components are soldered to. And then under the solder mask, which is the green stuff, you have traces, which are copper lines that connect different components. So once you solder components, they'll be electrically connected through the board, and you can get a lot better connections and less complexity, just more resilience. Now, you don't have to have, you can just have a 2-layer board, so components on the top, maybe components on the bottom, but you can go much bigger. So a common one is a 4-layer board. The typical layout is a signal plane, so that's just all of your components connecting to each other, a power plane, let me zoom in, a ground plane, and then another signal plane for more components. The way to transfer between planes is something called a via. So it's a drilled hole that gets filled with copper, and depending on the layout of your different planes, things can connect to it, and so components can burrow down to the ground depending on what they need. This is a slightly better diagram, but this is for a much more complex PCB. So I think this has not just 4 layers, but maybe like 4 more, so maybe an 8-layer board. But you can see it's got kind of resistive, insulative material between each of the layers, and the vias will drill through and connect to different planes as needed. So designing the PCB, you draw your dimensions. So we want kind of a 20 by 20 millimeter design. That was purely arbitrary, just wanted to make it pretty small. And then after that, we are going to place our components. I'm just waiting for the GIF to loop because they all play at the same time. That's fine. Your components get dragged in as one big blob, but you don't want to place them all at the same time. Please loop. Yeah, it's not going to. 1 second. But in terms of layout, you're just looking to place components that you need to connect together with the pins that they need to connect as close together as possible. It's really like a very trial and error kind of pursuit. But it can be fun moving things around and seeing how they play. Now, we have our microcontroller driver on one side of the board and then our LEDs on the other side. So you can flip components to the back and they'll show up as blue, and then you can place them on top of anything else and they will be on opposite sides of the board. Now, you could place them individually, but there are tools that let you do stuff like grids. So I'm still learning a lot of the layout tools. So my first boards were done fully by hand, but there are tools and functions to help you. OK, so connecting 2 things on opposite sides of the board, we've got an LED on the back and a LED driver on the front. So we're going to use a via. You can see here, we've got pin 8. And if we swap to the back, we can see we've got an LED right there that needs pin 8. So we're going to drill a hole through and then route both of those components into that hole, and so they connect. And then we're basically going to do that for the rest of the pins, and hoping that things don't clash. For the power plane and ground plane, we can select the different layers. There's front, 2 middle ones, and back, and then we can define a ground or a power. So this is our final design, and we've placed supporting components near the components that use them, made sure that everything is separate, and there is an automated checker, like a DRC, and we can run that and it will tell us whether or not we have any issues, unconnected pins, grounding problems. We only have 1 error, so we only have 1 warning, so we're going to continue. But I didn't just go from start and then have a design and it worked fully. I had to iterate on this multiple times. This was my first design. It kind of looks like some bugs, which is kind of cool. But the problem is a lot of my top layout was not using space, and it was extremely crammed. I couldn't fit things in for my USB-C, so I had to put it on the opposite side. So I tried again. This was my vibe. I tried having a go, just vibing it out, and it was even worse. I don't think all of the components are even represented here. And I tried again, focusing on just direct connections, and this one worked a lot better. OK, so now we've got a design that should work. we can go and make the boards. I don't want to deal with ferric chloride or wearing hazmat suits or anything like that, so I'm not going to make the boards myself. I'm going to get a factory to do that for me. But luckily nowadays, low volume boards are like really cheap and very quick. For a 4-layer board, you can get it around in a week or 2, and it costs you next to nothing. Here's my costs. If you were wondering, the components are like cents each. I mean, the USB-C and the LED driver were the most expensive, but the resistors, you can buy hundreds for like $10. It's crazy. And then for PCB fabrication, $2 for the board, $3 for the solder stencil, which we'll get to later. It's extremely cheap. The microcontroller I used was like this famously 10-cent microcontroller, like cheapest on the market. I bought it off AliExpress for 40 cents, which was a ripoff, so learned from my mistakes. I'm a bit embarrassed by this part. Shipping costs for the first and second piece components, I ordered them separately, so it was $24 a go, and then $11.18 for the 2 board runs I did. But I bought in bulk, so I ended up getting about 1,000 different components, which roughly translates to 5 cents per component. So I'd say the shipping was almost negligible. So in total, without shipping, 1 board would be about $9.50, but that's including the stencil, which you can use on multiple boards. So we're looking at about $6 each assembled board. This is super cheap, but for high-end boards, like the stuff in iPhones, you're not going to be getting this low of a price, and you're not going to be able to assemble it by hand. So this is the motherboard from the iPhone 17. What they've done is that they wanted more than just 2 surfaces to place components on. You can get boards that will place resistors and components inside the actual layers, sandwiched between internal layers. But for bigger things like CPUs, you're going to need an external surface. So they've actually taken 2 different boards and then soldered them together at the edges to get this sandwiched effect. So these things are not really available for hobbyists or individuals, or they'd be just prohibitively expensive. This would also be assembled automatically. So there are pick-and-place machines, which will automatically grab tiny components and place them exactly on the boards where they need, and then the whole thing can be automated. And I could do that. Like the factories allow automated assembly. It's about $12 per 5 pieces. So for me, it would be quite expensive. But also, the reason I didn't want to go with this route is assembling the thing is like the only physical part of this whole process so far. Everything else has been designing on a computer, so I haven't really met my goal of getting out and about and dealing with physical things. So I really wanted to learn how to assemble it myself, which also gives you skills to be able to debug or reroute or repair things and just understand a bit more about what goes into the tech products that we all use. So skill number 3. Microsoldering. Since it's a physical pursuit, you're going to need tools and we're going to need some space. I converted my entire closet, or most of my closet, into an electronics workshop. Yeah, I only have like 1 chest of drawers. Everything else, all my other clothes had to go. But here's what we're going to need. So number 1, absolute must, is a microscope. These components are tiny. And I thought I was terrible with my hands. I'm, bad handwriting, maybe shaky hands, but having a microscope allows you to manipulate things at a much smaller scale very easily. So we're going to need that. And we'll need to have some tools to perform the actual soldering. So a good small-tipped temperature-controlled soldering iron, a soldering hot plate, and a heat gun are definitely necessary, at least for my project. I bought a ton of tweezers. Turns out you don't need lots of low-quality tweezers. You just need 1 good quality tweezer. So just buy something. This was like $10, and it's like 20 times better than anything else. And we'll need some supplies. So we've got solder wire, solder paste, and then flux. Flux is a chemical compound. It is usually built into other solder products, but it helps disperse heat and prevent oxidization, which can form crusts and get all gunky. And then finally, we'll need some other tools, like a toothbrush, a knife, some alcohol, and some helping hands. Now, the assembly. First part of the process is getting the solder paste exactly where you want it. I used a razor blade. I don't think this is necessary. You can probably just use any flat piece of metal, or even your credit card if you if you want solder paste on your credit card. But we need to get the stencil exactly over the component's footprint. So this is actually the hardest part of the process I found, because you need to lie them both flat, and then you need it to not move during the entire process. So whether that means sticky taping one side of it, so you can just have it locked in, or I found that using some tweezers to hold the side works as well. Get your solder paste on there, and then use your knife to squeeze all the solder paste specifically into the holes. Now we've got our solder on the board. We're going to be starting to place components. These things are tiny. I used 0402 components, which are like kind of the second smallest generally available components. And they are like large grains of sand. So getting them exactly where you want them to go is very hard. And sometimes you'll squeeze a bit too hard, and they'll slip out and just ping off across the room. So it's really good that they're so cheap. This part doesn't need to be perfect. You can kind of align things generally as long as they're kind of over the right spot. And then put it on your hot plate, and there are specific heating curves that the hot plate will have to melt the solder at the right pace. And this is a really satisfying part. You can watch it go from the paste into melted solder, and it will pull all of the components to the pads that are basically producing the heat. So really fun, and everything just like neatens up and looks great. So you don't really need to be too precise about where your components are actually placed. All right. Now, we got to get this thing running some code. This is, I put a test point on my controller, and that is connected to a wire, which is connected to a real programmer. And this thing is the thing that will send signals to my board to make the microcontroller accept my code. But we do need some software. Luckily, we're all software engineers, so we can skip this part. It's pretty easy. No, I'm kidding. It's really hard. This is one of the most difficult parts. Honestly, embedded code is still a mystery. I'm not sure if that's because I'm more familiar with other software, and so I see the parts that are difficult. I know what I don't know, that kind of effect. But the requirements of how to get things working without using example code is still a bit of a mystery to me. I'm not going to go into like that part. I'm giving you guys a bit of a break from software during this talk, but this is kind of how the code should function. The microcontroller has a loop. It will update the design that we want to send. It will send that data using a protocol, and then it will tell the driver to display it. That goes through 3 different pins. We've got a clock that is consistently ticking at a certain rate, and then we've got the data, which goes from high and low voltage depending on the data that it wants to send, and then we've got the latch that can operate at the end. So you can kind of see that's going like that. We've got a code. We've put it on the board. Vast simplification, but now we get to see if it runs. This is moment of truth. No. Okay. So this was actually my first time plugging it in, and it did nothing. which means it's time to double check everything. Because there's no observability into the actual code that's running on the system or any of the connections between the components, it is super easy to just immediately go into a state of despair and get very sad. So about 4 days was me just trying to rack my brains around why this wasn't working. And you're gonna need tools. So I went and bought myself an oscilloscope. Not just for this project, I wanted it generally, but it is super useful to see the voltage over time and see what the microcontroller is sending and what the voltage at different points are. So you'll need one of that. And many days later, I figured out it was a core misunderstanding of how the LED driver was actually working. I thought it was providing power to the LEDs, but in fact, it was pulling power through the LEDs and then connecting them to ground. So my whole board was backwards, basically. To validate that assumption, I did this, which is a monstrosity. This is connecting from a central 5-volt signal and then an individual wire going to every single LED. But it works, yay! Cool, so now we know what's the problem and we've got a working board. We can actually finish this, which means making a case and making it look like something of a product and not just a PCB. Requirements for this, the original product was injection molded. So it's when you get mold and you insert plastic into that at very high temperatures, very high pressures, and you get a nice looking case. So I went out and got a Engel eSpeed 500, thin-walled injection molding machine. No, I'm kidding. These things, even just making a custom mold is tens of thousands of dollars. So there's no way I'm going to do that. I'm going to go for 3D printing. So I picked up a 3D printer just for general fun earlier, and it is great. Like, it opens the doors to experimenting with design and form. So it's really fun, but you're going to need to learn how to do 3D modeling. So skill number 4, all right. This one's quite challenging because usually when you have an object that you're trying to make, you just want it to appear. You say, I want a cube and I want it to have holes, and maybe in Blender or something you can do that directly. But for working with physical constraints, you're going to want to use a parametric modeling platform, maybe like Fusion. And the thing that Fusion does is it lets you define measurements and then relationships between measurements. So you could say, I want my holes to be this big, and because they're that big, I want them to be spaced evenly. If you change the size of the holes, then the space between them will change as well. So you can go back and tweak things, and you don't have to redesign the whole thing. When you're working with Fusion, you're going to start with a 2D object, and then you're going to bring it into the third dimension using extrusion, so pulling it out into a cube, or removing stuff using that 2D shape. We need some internal areas, so I went with a kind of a outer case and then a inner. The inner part basically separates the pixels from each other, so it's not just a white blur. Each pixel is getting its own LED light shone on it. And then I had a plate where the USB-C can stick through at the back. And I added the designs from the original IKEA product. Putting it together kind of looks like this. So I also could have printed a diffusion plate at the front, but I went with just frosted acrylic and cut that out with scissors. Not the most high-tech, but does the job. And then our diffusion grid goes in there. Our circuit presses into the back plate and then just press fits in. You can go into like adding clasps and things with 3D printing, but I just wanted to keep this simple. And as long as you don't throw it at the wall, it shouldn't come apart. So here it is, and I've got one right here. It's quite small, and it looks tiny compared to the original. And the little program I can show you on here as well just runs a randomization pattern with a nice little fade between. So I just wanted to get this project working. It's very simple what it does, but I think it's a very nice desk ornament, or like, nothing too flashy. I'll just put that here. If you want to come and see it afterwards, I've got a couple. So this whole process, this was costly and time-consuming. As most hobbies are. Like, if you want to get into something that costs more, then you could find hobbies. Buying a racing bike, I'm sure, costs more than this whole process. But compared to software, there is that consideration. Being a software hobbyist is basically completely free. But I think it was, if you're interested in this kind of thing, you can make functional products, or you can make just things that make you happy, art, tools. There's so many different possibilities, so many places to get inspired. I would recommend picking an easy project and jumping in. There's tons of fun parts. I loved online shopping and buying stuff from AliExpress. Like, receiving packages every couple of days was really good fun. It feels like Christmas. PCB design, also therapeutic. Routing traces between things is like connecting the dots. It's very cool. Watching the 3D printer work really feels like you're in the future. You see this kind of factory-looking thing just going away in your room, like really interesting. And then just having something tangible that exists because you made it is super satisfying. So I would absolutely. I'm going to improve the design. I'm thinking of doing some battery logic and having it self-contained and kind of turning it into a little keychain type thing. But even if it's in its current form, it brings me a lot of joy. And if you want to see any of the resources, the whole thing, all of the models, all the code, and the slides are on my GitHub. And there's a link. These slides are hosted, so you can scroll through them on your phone. Or if you want to take a closer look and have a chat, I'm sure there might be electronics people out there in the audience. So if you've noticed anything that I could learn from or improve, please come find me. We'll chat. But other than that, that's it. Thank you very much.
Just opening it up to the floor. There's any questions for Drew? Just going to race around. Got little legs.
Go, go, go.
Yeah, how you going? Have you fallen down the rabbit hole of making your own keyboard yet?
No. I did do some mechanical keyboard builds. I haven't done any PCB design for that, though. So
Let me show you mine after this, then.
I would love to do that. Yes, please.
Very fun.
Any other questions?
We got one.
Just we need it for the recording.
Thank you. Yeah, great talk, Drew. Yeah, really demystified a lot about that domain. I was curious, after this, do you have any ideas about a next project that you'd like to work on?
So this project was like a little derivative. I'm remaking a product that IKEA already sold. So I would like to build a similar kind of object with digital properties, but I'm not really sure what kind of shape or look that will be. Probably something to do with pixels and screens, but we'll see.
Okay, and the one at the back here.
Hey, yeah, great speech, Drew. Actually, quite a lot of work went into that.
Yeah.
And I'm sure everyone appreciated that. So I wanted to ask, you said there was an issue, so the lights weren't turning on, and then you wired everything. So
Yes.
what was, like, how did, like, I didn't understand that part.
Yeah, yep. Okay, so when I was looking for my component, the LED driver, I just bought something that said LED sync driver, And apparently they don't just put random stuff in the title, it actually means something. So a sync driver, it doesn't send voltage. So normally when you're powering an LED, you have, say 5 volts going out through the LED and then back to ground. And that energy will impart, in the LED and it'll turn on. You have to have it going the right way, though, so an LED is directional. My circuit went power coming out of the driver through the LED, and then the other side of the LED was connected to the ground. But a sync driver provides a connection to ground. So basically, I was having ground on both sides of the LED and no power anywhere in the circuit. So when I hot-wired everything, and I can show you that, this is going to be hard. Yeah, so after I hot-wired the janky, I can't find it now. Let's back up. OK, I'm lost. So after hot-wiring all of my pins, I basically had to unsolder them, and then, yeah, there we go. So I had to unsolder all of the LEDs, flip them around so that the opposite side that I was connecting to the driver was connected to the ground. Sorry, I had to flip all the LEDs, and then I had to add a connection to power for each of them. So ridiculous. Never do that. Just like order new PCBs. But I had some time while I was waiting. Yeah. Thank you. I need sleep now. Yeah.
Put your hands together for Drew.